Hi everyone. Sorry that I'm not able to give lecture live today. I just want to be able to make sure that I can actually talk through the whole thing, and this way you can go back and rewind and rewatch anything that you might need to in order to understand it. So I'm going to be making two videos. One of them is about the theory of lines in 3D space, which is what section 1.6 is about, and then I'm going to go over some examples. Okay, so lines in 3D space look like this visually, and they're different from vectors in a couple ways. You can notice one of them is that they extend infinitely in both directions, and another thing that's different about them is you have, unlike a vector, which we could say this and this and this are the same vector as long as they're pointed in the same direction and have the same magnitude, this line we would say is different from this parallel line over here, right? Because the position of it matters. So we kind of we anchor it at some point, and we say that's enough to define it. So speaking of defining a line, I'm going to try to work my way up to tell you how how we get the equations of a line. But we need two things. We'll say for the equation we need, so for the equation of a line in 3D space, we need a point on the line, right? Two things, right? We need a point on the line, and we're going to use the same notation as we did for a plane. So we need a point on the line, P naught, and we need a direction vector. Right, so a slope isn't going to cut it, because if I, in 3D space, if I say this line starts at 1, 1, 1 and it has a slope of 2, not enough information. So we need a, tell me how far it's traveling in the x and the y and the z direction. Okay, so that vector, I'm going to call it u since that's what the book calls it, but that's going to consist of an a, b, and c. Now, don't confuse this with a vector that you might see in a plane equation, right? That's a normal vector, but this is a vector that defines a line. So in the example here, here's a line, here's a point on that line, and then a direction vector might look something like this. Right, so that direction vector says, hey, this line goes in this direction. Now, something you may notice right away, and we'll get to this, is that if you take this u vector and you point it in the other direction, so if you make a negative u vector, right, that also would define that line, right? Because really we just need one direction, and then we'll assume that it travels infinitely in the negative opposite direction as well. And in addition to that, you might notice that just like a normal vector, 2u, right, 2 times u would also be a valid direction vector, right? We start at this point and we travel 2u. That gives us a definition for that line as well. So just like planes can have a lot of different normal vectors and a lot of different points on the line or on the plane, this line can have a lot of different points on the line, so any point on the line, and then any direction vector, as long as it's pointed in the same direction as that line there. Okay, so let's figure out how this equation is going to work. So I'm just going to redraw this here. So here's my line. Here's my point, P naught. And here's my vector, U. Just giving me a direction. Okay. So, if I want to define a point on the line, here's my strategy here. I need to add up some vectors. So I'm going to kind of give myself a miniature x, y, and z axis. Right? So I can say here's the origin. So here's the origin. I'm going to label that O. Right? If I want to define a point on that line, I'm going to have two vectors here. The first vector is going to be this one here to kind of get me to the point P naught. So it's going to seem a little silly because we have P naught is equal to x naught, y naught, z naught, and then this vector O P naught is going to be x naught minus 0, y naught minus 0, z naught minus 0. So just x naught, y naught, z naught. Okay, so that's my first vector pointing from here to here, right? O, origin to P naught. And then the second vector is going to be some scalar of u. So just 1 times u is going to give me this thing here. That's a point on the line. 2u, so OP naught plus 2u would give me this point on the line. OP naught plus negative 2u would give me that point on the line, right? So to make that nice and generic, I'm going to say this vector is going to be some scalar of u. So I'm going to use 2u in my visual example, but looks like that. So this is some scalar of u. And the point that I reach here, just like the plane had a generic point P, I'm going to talk about this as a generic point on the line. So P is equal to x, y, z. Here's x naught, y naught, z naught. This is x, y, z. Okay. All right. So remember when we add vectors, vector A plus vector B visually looks like this, right? When we add them tip to tail, we get this vector A plus B, right? I'm going to make a vector. Actually, I'll leave that up. I'm going to make this vector here. So this vector is OP naught. This vector is OP. So hopefully you can see what I'm going to do is I'm going to add OP naught and I'm going to add this vector here, which is going to be some scalar value t times u. Right, so some value, some scalar times t is equal to OP naught. So, or sorry, OP rather. So maybe better to write it out here. OP naught vector plus some scalar t times u is equal to this vector OP. Okay. I promise the equation is easier, but it's once you kind of get everything together. But I just want to be super clear that this is where this is coming from, because it's going to be important to think about, changing this t value later on. All right. Anyway, when I break this down, we already said that OP naught is this thing, x naught, y naught, z naught. T is just some letter. We'll save that for a second here. This u vector, remember this is an ABC, right? So this is our direction vector, right? So get to a starting point, move some amount in our direction, this plus this is equal to this vector OP. OP is the vector x, y, z. All right. If we take these individual components here, we get that x, we get that, let's do it this way, that x is equal to x naught plus at, right? It has to be that all of our x components have to line up, t plus this, or t times that. Y also has to be y naught plus b times t. Z has to be equal to z naught plus ct. These three equations together is what we use to define a line. So we'll say these three equations all together define a line. Okay, so we're not able to fit it all into one equation. We just give ourselves three equations to work with. So I'm going to go ahead and put a box around that. Just a quick example, so you can see it's an action, a line that goes through the point. One, two, three, and is so I could say this a couple ways. I could say the line travels in the direction 4, 5, 6, or I could say that it's parallel to the line 4, 5, 6, or sorry, parallel to the vector 4, 5, 6. So I'm going to use that language just to give you that direction. So it goes through the point 1, 2, 3, and it's parallel to the vector 4, 5, 6, has the equation okay, so we'll define them like this: x, y, and z. X is equal to, so here's my point. This is my x naught, y naught, z naught. So I'll say 1, 2, 3. And my vector that tells my direction of that line is a, b, c. So I put those numbers there. We can do a couple things with this line. So say let's use this line to explore some ideas. I'm going to do a couple things. Let's say like find a so let's find a second point on the line. We have the point 1, 2, 3. But let's find another point on the line. To give that same drawing again, remember we've got this line here, right? Here's my line. Here's that point on the line. Here's 1, 2, 3. And we know the direction that this line is traveling in is 4, 5, 6. So that vector, if we line it up there, right, that vector there is the vector 4, 5, 6. So we know from being able to make a vector out of 2 points, or if you're given a point and a vector, you can find a second point on there. We could say a second point, this one right here, this would be the point 1 plus 4, 2 plus 5, and 3 plus 6. All right, so maybe I'll draw that over here. So this point Q, Q is equal to 5, 7, 9. Right, that's one other point on the line. Right, this point right here. We can also test to see if the point 6, 8, 10 is on the line. So again, we know the equations for these lines. And we can use this equation to test these x, y, and z values. So here's the test, right? So we get we can say 6, 8, and 10. These are like our new values that we can plug in here. 1 plus 4t, 2 plus 5t, 3 plus 6t. If we solve for these, we end up that we get that what t is equal to 5 over 4. This time we say t is equal to 6 over 5. And here we get t is equal to 7 over 6. Right? Each time I'm just solving for t in each of these individual equations. Unfortunately, we have a mismatch this time around. If we got the same value each time, that would tell us that we were looking at a point on the line, but here we could say that, or we can conclude that 6, 8, 10 is not on the line. In fact, if any of those numbers didn't match perfectly, that point is not on the line. So we'll say only if all 3 t values match. Another thing we could do is, well, I guess now that I've shown you this sort of setup here, if we pick a value of t, we can find a third point on the line, let's say. Here, if you look at the original equations, we really just sort of picked t equals 1. Right? 1 plus 4 times 1, 2 plus 5 times 1, 3 plus 6 times 1. We could have picked some value and say t equals -3. That would be a point maybe over here. Right? Still on the line. So this point here would be, let's call this point R. Maybe put it this way. X is equal to 1 plus 4 times -3. Y is equal to 2 plus 5 times -3, right? Just going off of this formula here. Z is equal to 3 plus 6 times -3. So we would get, in this case, 1 minus 12, so -11, 2 minus 15, -13, and then 3 minus 18, which would be -15. So that point there would be -11, -13, -15, because that's our x, y, and z values. Okay, so just another path to come up with that point there. Okay. In fact, if we think about what this t is doing here, that t is really sort of scaling this. We're sort of sliding along the line here, right? This is when t equals 0 at our starting point. Here's when t equals 1. That gives us this point. T equals 2 would be here. This point we found back here. T t equals -3 back here. So anyway, all right. So that is how to find another point on the line, or you can test to see if a point's on the line. We can also find a parallel line. So again, just a reminder, this is our formula. 1 plus 4t, 2 plus 5t, 3 plus 6t. Thinking about what makes this parallel is the fact that it is traveling in the same direction, right? So we can use that intuition that we've got to say, here's a line, they're direction vectors. If they have the same direction vectors, right? Here's a direction vector, here's a direction vector, right? That would make these two lines parallel to each other. But you may have already guessed that it doesn't have to be the exact direction vector. We could have two parallel direction vectors, right? So maybe this line has this point over here and this direction vector, and this line has this point here and this direction vector. So as long as we have parallel direction vectors, we can have two parallel lines. Okay, so so example 1 might be the line x, y, z. So I'm going to make sure that my 4, 5, 6 stays intact. That's the same direction. But I'm going to pick a new point here. I want to be careful to pick a point that's not already on this line. So for example, for my new point, I wouldn't want to pick -11, -13, -15, because that's just the same line as what I've got here. So I'm going to pick 1, 2, and then I'm going to change this one to be 10. Right, so say new point, same direction vector. Just to show you that it's not a matter of just changing one of these numbers, I could also say this is 11. All right. So anyway, I just wanted to make sure that I wasn't picking something that was also on this line as well. So anyway, this is parallel, right? Another one might be a line parallel to that would be this one. Say x equals y equals z equals. So I'll pick a new point here. Let's say 1, 13, 50. So a new point, right? A new x naught, y naught, z naught on here. And then instead of 4, 5, 6, I'm going to try this one out. I'm going to say instead of 4, 5, 6, I'm going to go with a negative version of that. I'm going to say -8t, -10t, -12t. Right. So you can see how I've got this 4, 5, 6 here. I just multiplied that by -2. So here I've got a new point, 1, 3, 50, and I've also got a parallel direction vector. All right, so maybe a better name these. So we'll call this line 1, line 2, line 3, and we'll say lines 1, 2, and 3 are all parallel. So very quick and easy way to figure out if two lines are parallel to each other is if they have this parallel direction vector, right? Another thing you can think of is if two lines intersect. So here's line 1 and line 2. Let's say line 1 where this equation is our familiar line. And this line here will be, let's say, so I'll kind of give it to you the way the book might say it. So this would be 10 plus 1t. 10 minus t and 8 plus t. Okay. Now, one way to think about these two lines, if you think about a system of equations, right? This is a system of 6 equations that you might want to solve. And that is there is a possible way to do that, right? I'm not saying it's impossible to do that, but an easier way to figure out if two lines intersect in 3D is going to be let's solve this by finding the distance between those two lines. So just to give a little bit of motivation for this, if you see in 2D space, right, we've got this line here and this line here. Let's say they're parallel. They never intersect. If they're not parallel, at some point they're going to intersect. All you have to do is figure out where is that happening in the x, where is that happening in the y. I'm sure it's something that you've done in an algebra class before, right? The problem in 3D space is you can have a situation where two lines are not parallel and they also don't intersect. So I'm going to draw a line here on the left wall, so to speak, right? This wall over here. So that's going to be this line right here. Third time's a charm. Okay. So this line here, and then my second line, I'm going to draw kind of going straight through the y-axis. Right. So these two lines, even though visually we can see some overlapping here, if you can picture the same thing I'm picturing here, x, y, z, right? These lines are skew. So skew means they are not intersecting. And also not parallel. So determining if two lines intersect in 3D, actually it turns out that the easiest way that you can do that is to just figure out the distance between them. And if the distance between those two lines ends up being 0, that means they intersect. But we can also use the same process to figure out the distance between two lines. So again, with all distances in mathematics, we're not looking for just some random distance between one point and the other. We're looking for this minimum distance. So let's find the minimum distance between these two lines. They're probably going to be skew lines, right? So if the distance happens to be 0, then they intersect, but either way we'll be able to figure out whether or not those two lines intersect. So the process goes like this. So if we have two skew lines, or we'll say two not parallel lines, what we can create are two parallel planes. And those planes are each going to contain one of these lines here. So what we can do let's create plane 1 plane 2. Might as well call this one plane 1 since it's on the left. Oops. There we go. There we go. So plane 1 is on the left. So we take two non-parallel lines and we create two parallel we create two parallel planes. Containing those lines. And then we find the distance between those two parallel planes. So we saw the formula for this one, right, already. Okay. This one, if we're trying to create these parallel planes, again, they should have similar normal vectors on here. This normal vector, we can kind of picture it connecting these two, right? This normal vector, right, sticking out of the plane, right, sticking out this way or sticking out this way, depending on how you look at it. This normal vector sticking out of the plane is something that's perpendicular to this line and perpendicular to this line. So we can say that the normal vector, we can even say the shared normal vector, between these planes is the cross product of the line's direction vectors. So that sentence is kind of a lot to take in, but here's a direction vector on this one. Here's a direction vector, let's call it V, on this one. When we make these two cross each other, when we take the cross product of U and V, that's going to give us this normal vector between them. Okay, so I'm just going to copy this and bring it down here, and I'll show you the whole process. Or in theory, I'll show you what it is. In terms of the actual example, I'll do that in the next section here, because we do deal with that. But this has a direction vector we can call this one U 4, 5, 6. This one has a direction vector -1, -1. Actually, I'm going to keep this consistent with my 1 and 2 here, so I'm just going to rename this. Sorry about that. Call this one U, call this one V, just so there's no confusion there. Again, the names don't matter. I'm just assigning names so that we have something to call them. Okay, so direction vectors. My normal vector is going to be U crossed with V. For both of them. If I want a point on the plane, point on the plane is going to be 1, 2, 3 for this one. Point on the plane for this one's going to be 10, 10, 8. From here, we have enough information to make two planes, normal vector point, and the distance between them will be, so I'll say plane 1, plane 2. After this point, we can figure out the distance between them using that formula, which I laid out in the last video. That's going to look something like this. Okay. All right. There is one other thing I want to show you, and that is something called symmetric form. So when you think of an equation of a line, I want you to think of these three equations. Right? That's, in my opinion, that's the most useful form, and I want you to easily recognize that. There is another way to write down lines. We have this form, x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. That's the way I want you to think of them. This is called the parametric form. Yeah, that's my preferred form. Another way to think of this is if you solve for each of these in terms of t. So I'll say solve for t. This one is going to become t equals x minus x naught over a. Algebraically, right, z minus c naught over c. So if you solve each of them for t, and then you set equal to each other, right? Since if they're all equal to t, all of them should be equal to each other. Maybe I'll do that. Maybe I'll say solve for t up here. So if you set all these equal to each other, since they're all equal to t, you should end up with x minus x naught over a plus y minus y naught, or sorry, these are all equal to each other. Y minus y naught over b is equal to z minus z naught over c. So this is what we call symmetric form. The reason I'm not a big fan of this one is because, first of all, it's a three-sided equation. So you're going to have to do some work to figure out, basically everything that's not testing a point, right? And x, y, and z is going to be a little tougher with a three-sided equation. Another thing that I'm not fond of is, let's say that a is equal to 0, and that's totally fine. You could have a direction vector 0, 1, 1, right? That's a valid direction vector. Then you're dividing by 0, and you, of course, know we don't like doing that in math. So I will put a little caveat here. I'll say example. If, let's say this is 1, 0, 2, then b is equal to 0, we would write, we would say x minus x naught divided by 1 is equal to, and then for the 0 we skip over the y, so c minus c naught divided by 2, and then we put a comma after that and say, well, let's not worry about b, because, or let's not worry about the y component of this, because it's not going to change, right? It's sort of like a horizontal line if you want to think about it in 2D. So then we would just say, well, then y is equal to y naught in there, and it doesn't change, right? It just stays at that point, whatever it is. So anyway, just a little side note here, kind of an awkward way to define a line, but you should be familiar with lines that look like this, right? So if you see a three-sided equation like this is what they're talking about. Okay, I think that's all I wanted to say for the theory of lines. So big concepts from this are just seeing if lines are parallel, right, based on their direction vectors, and kind of the general outline for how we find the distance between two lines. I'll give an example of that in the next video, and then this set of equations for lines, right? Very, very important to have this. Okay, so that's enough. That's enough for this one. I'll see you in the next video where I talk about the examples.